So yesterday we have discussed about the characteristics of DC motor. Okay, and there are three different types of characteristics. So the first characteristic is the torque versus armature current characteristics, and the second one is the speed versus armature current characteristics, and third one is the speed versus torque characteristics. Okay, so we will discuss about these characteristics for three different motors. So we have finished the torque versus armature current characteristics of a shunt motor. Okay, so in shunt motor, the torque is proportional to Ia only because the flux is a constant parameter, and therefore the torque is proportional to Ia. So it is a direct linear relationship. So this green line indicates the characteristics of a DC shunt motor was for the torque versus armature current. And this dotted line, this line is the uh, shaft torque. Okay, and this is a gross torque armature torque developed. This TA is a gross armature torque developed, and this TSH is the shaft torque across the load. So at the time of no load condition, so TA naught, so TS is equal to TA naught because some small amount of the torque which is developed to overcome the stray losses present in a machine. These losses are always constant. So these are constant from no load condition to full load condition. Okay, and we have also seen the speed versus armature current characteristics. So your speed is given as n is equal to V minus Ia Ra by phi, and for the shunt motor this phi is constant, and your speed is proportional to now V minus Ia Ra. And for a constant applied voltage, whenever you change the Ia, then the drop Ia Ra drop will be increasing, and therefore the net speed of a motor gets reduced. Okay, so the speed in a reduction in the speed is very small as the armature resistance is small, and the drop in the armature resistance is also small. So this is a very small drop reduction in the speed from the constant value. Okay, so because of these reasons, this shunt motor is called as a constant speed motor. Okay, and next one, the torque and speed characteristics. So the speed torque characteristics of a shunt motor is given by this relation again. So this is at a no load value, and the speed is also constant. Okay, as the load on the machine increases, the load on the motor increases. That means that your torque is increasing. The torque is increasing, and because of this, your speed gets reduced. As the load on the motor increases, your speed gets reduced. Okay, so this is a reduction in the speed when the torque is increasing. So this is about the speed torque characteristics of a DC shunt motor. Now we will discuss about the torque and armature current characteristics of a series motor. So first of all, we need to write the equation for the series motor. So in case of a series motor, for series motor, the flux phi is proportional to armature current. Okay, because the series field winding is connected in series with the armature circuit, and therefore the flux which is proportional to the armature current. And the torque developed in a machine is nothing but torque T is proportional to normally phi into Ia, and therefore for series motor your flux is proportional to Ia, and therefore torque is proportional to Ia square. So this is the square of the current. Okay, and this characteristics is just like, yeah, this is your armature current, and this is your torque. Okay, and this characteristics is like parabola. So because it is a sphere, so it is just like a parabola like this. And here, after reaching certain point, if you goes on increasing the current, but your flux may not increase. Okay, so up to this point, your torque is proportional to Ia square. Once it is reaching the saturation point, saturated point, now your flux is going to be constant. Okay, so in this case, your flux, the motor cannot generate any flux or develop any flux, and therefore at this instant, now the torque is proportional to only Ia, and therefore it is just like a linear line. Okay, so this is nothing but your armature torque. Okay, and similarly, we need to draw the shaft torque. If I want to draw the shaft torque, and this will be like this. So this is a parabolic line, and this is a no load condition where the current is Ia naught, and this is your 0. Okay, and after that, again, this is reaching a particular value of current. Okay, and then now at this point, again, it is a straight line. Okay, so or you can represent this by dotted line only. So this is your TSH. Okay, so this is called as a point of saturation. Point of saturation. Okay, so this is also the point of saturation. Is it clear? So this is the torque versus a characteristics. Is it clear or any doubt on this?
Clear, sir.
Okay, nice. Next, let us take the speed versus armature current characteristics. So first of all, we'll write the equation for the speed. The speed n is proportional to the back EMF divided by the flux, or this is also proportional to your V minus IA RA by, and also this equation for the series motor, your back EMF will be nothing but your IA into RSC also. So divided by flux. Again here, for the series motors, your flux is proportional to armature current, and therefore flux is proportional to armature current IA. Okay, and in this equation, your numerator values, this IARA and IARAC are very small, and therefore this component as compared to your applied voltage, this total value will be very less. So in the numerator, this is a dominating value. The voltage is a dominating value, and we are keeping this V is nothing but your supply voltage. This is a constant. Okay, and therefore your numerator value is almost constant value, and therefore in series motors the relation between your speed and armature current is like this. So here the speed is inversely proportional to your armature current. The speed is inversely proportional to the armature current, and therefore what must be the characteristics here? How it looks like? This characteristics will be looking like this. Here, this is the speed if I take, and this is your armature current IA, and this is your speed. Okay, and the characteristics will be given like this, because whenever IA is equal to 0, whenever IA is equal to 0, your speed is going to be infinity, and whenever IA is infinite, then the speed is going to be 0. So that's why your speed versus armature current characteristics will be like this. Okay, and this is the inversely proportional characteristics. Okay, so here you can see that for the small values of small values of currents, the speed is very high. Just you can see that here. You can write it for small values of IA, speed is very high. Speed is very high. That means if I let us take that the machine is operating under no load conditions. Okay, let us assume that series motor is running under no load condition. No load condition. That means that your current IA will be equal to 0. Therefore, IA will be 0. So as IA is 0, your flux is also 0, and your back EMF is almost constant, because no load condition your speed is almost equal, so it is constant value, and therefore as per the relation n is inversely proportional to the phi. Okay, as this is 0, this is almost equal to infinity. The speed is infinite, so that means that under no load condition, or at no load, your flux is 0, the speed is at no load, speed is dangerously high. Dangerously high. It is infinite value, so it is dangerously high, and therefore, the main important conclusion is that DC series motors never run under DC series motors never run with no load condition. Never run with no load condition. This is a very, very important concept. Okay. A conclusion from this characteristic is that the series motors should not be run under no load conditions. Therefore, it is always run with a certain amount of load or full load must be applied on that DC motor. Then only your speed will be in controllable limits. Okay, so here if you see the belt driven drives, so belt driven motors or drive, so in that application, belt driven applications, just you can see that belt driven applications, your series motors will not be used. Okay, so DC series motors cannot be used for belt-driven applications, because whenever there is a slip in the belt, then the total load will be disconnected from the motor, and this motor will be run with a dangerously high speed. Okay, so this is an important point we should remember. Is it clear?
Yes, sir.
Yes. Then shall I go for the next one? No.
Okay, sir.
Then. So as we know that now the speed n is inversely proportional to Ia. For the series motor, we have derived this n is inversely proportional to Ia, and we know that the torque is also proportional to Ia square, and therefore your speed versus torque relationship will be given as n is inversely proportional to 1 by under root of t. N is inversely proportional to 1 by under root of t. And therefore here, whenever the load increases, so the torque increases automatically. The load increases whenever the load increases, the load on the machine increases, automatically your armature current increases and the torque increases. So as per this relation, n is proportional to 1 by under root of t. So as this t is increasing, your speed is gets reduced, and therefore this reduction in speed is also like this. So it is inversely proportional, and the torque, as the torque increases, your speed is gets reduced. And as per this also, this characteristics also, so for no load condition or for the smaller values of torque, for small values of torques, the speed is very high, and therefore this from this characteristics also we can understood that series motors should not be run with the no load conditions. Okay. And next, now let us consider the compound motors. Okay, so compound motors are of two types. The DC compound motors are of two types. One is cumulatively compound motor, and a differentially compounded motor. Differential compound motors. Okay, so in cumulatively compound motors, your resultant flux phi t will be equal to, it is a sum of phi shunt field flux and the series field flux. Okay, so the characteristics of these compound motors will be depends on the characteristics of the shunt motor or series motor. Because if the flux which is dominating in a particular machine, the characteristics of that compound motors will have the shape of our shunt motor or series motors. But here the shunt motors will have the constant flux, okay, and your series motors have variable flux, because as the load increases, the flux which is produced by the series field winding phi sc will be varying, but the shunt field flux is always constant. Phi sh is always constant, but phi sc is varying. Now if I make phi sc is constant or very less as compared to the phi sh, then the characteristics of your compound motors looks like the characteristics of shunt motor. Okay, and if you vary the flux, then phi SE in the flux in the series motor, series uh, winding, then the characteristics looks like your series motors. Okay, but the main advantage of your cumulatively compound motor is like uh, this can be run under no load conditions, but it is not possible with a series motor. So this is the main disadvantage of a series motor is that this series motor cannot be run under no load conditions, but your compound motor can be run under no load conditions because your flux which is produced by the shunt field winding produces the back EMF, and therefore your speed will be well within the limits. Okay. So if you take up differential compound motors, then the flux phi T will be equal to phi SH minus phi SE. And therefore, as the load on the machine increases, your phi SE goes on increasing, the net flux will be gets reduced. And because of this, then as the speed is very high, so because N is inversely proportional to the flux, so this motor may be run with a dangerously high speed, and because of there is a change in the flux with the uh, flux produced by the series field winding, and therefore the differentially compound motors are rarely used for any practical applications, as your flux is varying with respect to your shunt field flux and the series field flux, and your speed maybe gets very higher values, and because of these reasons this differential compound motors never be used, but your cumulatively compounded motors having the highest torque, because your torque which is produced in a series motor is proportional to Ia square. Okay, and therefore in the time of starting Ia is square of the current, torque is proportional to square of the armature current, so it is having a very highest torque as compared to shunt motor, and this series motors can be useful for applications where we require high starting torque, and as compared to this shunt motors, your compound motors will also have the more starting torque, because the flux produced by the shunt field winding and flux produced by the series field winding is added each other, aiding each other. Therefore, your net flux will be very high, and the torque developed is also high. And therefore, your cumulative compound motors can also be used where high starting torque is required. Okay. And therefore, now I will write here the characteristics of your compound motors as versus the torque versus armature current, because your torque is proportional to phi into Ia again. Okay, and here this flux phi is produced by the phi SH and phi SE, because this is a variable one. I can write this as a phi T. Okay, and if the flux phi SH is more dominating as compared to the series field winding, as compared to the series field flux, and therefore this is going to be constant. The characteristics are looks like shunt motor. So this is a, let us assume this is a characteristics of a shunt motor, because this is a torque for the shunt motor. Torque is proportional to Ia only, so it is a just linear relationship, and therefore this is the characteristics of a shunt motor. Okay, and this is the characteristics of series motor. So it is a parabolic in nature. So this is the characteristics, because for a series motor, torque is proportional to Ia square, so it is a parabola. So this is a series motor, and our characteristics for the compound looks like this. So if you take the cumulatively compounded motor, this is your characteristics. Okay, so this is for cumulative compound motor, and this one is for a differential compound. This will be okay. So this is the characteristics for differential compound motor, and this is for cumulative compound. Okay, so this is the torque versus armature current characteristics of a compound motor. Okay, next. Now let us consider for the torque and armature current characteristics. Speed versus armature current. So again, the characteristics, speed versus armature current characteristics for a so the speed versus armature current. This is IA and this is speed. So for shunt motor, the speed is shunt motor V minus IA RA. So here IA increases. Whenever the IA increases, your speed gets reduced. So at the time of starting, this is a constant speed. Always will have a constant value or constant no load speed, and there will be a small reduction in the speed for the shunt motor, okay, from the no load value in mind. Next, then what is a speed equation for series motor? N is directly proportional or inversely proportional. So this is inversely proportional to A, and here this is given like this. So this is the speed characteristics, speed versus armature characteristics for series motor. Okay, and therefore now your characteristics for the compound motor. So for the cumulatively compound, again this will be like this, because the speed is proportional to 1 by flux. Okay, so phi t is nothing but phi sh plus phi se, and therefore the net flux is increased, and because of this it is having a slightly reduced speed as compared to the shunt motor. So this is a cumulative compound motor. So this is the characteristics. So as the current rises, your net flux will be phi se increases. If you maintain phi sh constant, also phi se is increasing, and therefore the net flux is gets increased, and this is a V minus IA RA also. Okay, so as IA is increasing, then this drop will be increased, therefore the net value will be decreased as the flux is increased here, and therefore the speed is always decreases. So this is for cumulatively compounded motor, and for the differentially compounded motors, so this is the V minus IA RA divided by phi t. So phi t is nothing but phi sh minus phi se. So the net flux is gets reduced. Okay, so this net flux is gets reduced. Because of this, your speed will be increasing, and this will be increasing like this. So if the speed of a motor is gradually increasing and it is goes to the dangerously high speed. So because of these reasons, now your motor cannot be used for any practical applications. Okay, so is it clear? N versus IA characteristics. Is it clear or any doubts? Now, we'll have a speed versus torque characteristics. This it is also similar because this is operating as a torque now. This is nothing but a torque. Okay, as the load increases, your in the previous case also same. Okay, as the load increases, your armature current increases, and therefore the speed of a machine increases. So increases in this direction like this. For a differentially component motors, and similarly here, if you let us assume this is a constant value, this is a constant speed. Now there is a decrease in the speed. This is for shunt motor, and again this is for this characters, this dotted line. This one is for series. So this characteristics looks like same as in a previous case. Okay, so this is about the characteristics of all the generators. So anyone, if you have any doubts on this, just you can ask me now regarding the characteristics of motors. Is anyone has having any doubt?
No, sir.
No. Okay, now shall I go for the applications? Just note down all these applications. So the applications of shunt motors. So these are used for various machine tools such as lathe machines, drilling machines, and milling machines, etc. Because the shunt motor is having a constant speed. Okay, so it is always rotating with a constant speed. Because of these reasons, so they are used for the printing machines where we need to print any particular paper. Okay, this is also used in paper machines for the cutting of equal size papers. And centrifugal and reciprocating pumps, they are also running at the constant speed. And your blowers and fans, etc. These are running at a constant speed. So at these applications, we use the shunt motors. Yes. Have you noted all this?
Yes, sir.
The next series motors, and these series motors are having high starting torque, and the speed is also variable, but this series motor cannot be run under no load conditions because the speed is very high. And because of these reasons, they are used always in electric trains because all the loads are connected, all the bogies are also connected to the motor, so it can run it. Okay, and diesel electric locomotives, the cranes, hoists, trolley cars, and trolley buses, because every where they are having loads directly connected to your motors. Because of these reasons, your series motors are used for these applications. రాసుకున్నారా?
Yes, sir.
Yes, sir.
Then next, the applications of the cumulative compound motors. So they are having also the highest starting torque. Cumulative compound motors are also have high starting torque because the flux produced is proportional to the shunt field winding and also the series field winding. And the no load condition is allowed here. As in case of series motor, the no load condition is not allowed, but shunt field winding will produce the some amount of the flux so that the speed will be well within the limits. Because of these reasons, they are also used in elevators, rolling mills, planners, punches, and shears. And the last one, the differential compound motors. The speed of these motors will increase with the increase in the load, so which leads to an unstable operation. And therefore, we cannot use these motors for any practical applications. So, in any machine, as the load increases, the speed has to be reduced always. Okay, then only your back EMF is particularly operating and it will produce the currents and also torque to meet the load demand. But in differential motors, this is not the case. As the load increases, speed is also increases. So your motor will be unstable region. It is operates on unstable region. So because of these reasons, these applications are very rare. Okay, is it clear? And next, we will go through the speed control of DC motor. So what do you mean by speed control? So for any particular motor, the speed control is very, very important parameter. So in case of DC motors, there is a wide range of speed control is available with the help of your voltages and resistance and flux, because the speed is proportional to the applied voltage and also the armature voltage and next the flux. But this is not possible in case of AC motors. So AC motors are always run set at the constant speed. So the speed control is not possible for the AC motors. And here, speed regulation. There are the two terms we'll use: the speed regulation and the speed control. So the speed regulation is different from the speed control. Speed regulation is nothing but the change in the speed from the no load condition to the full load condition. Okay, so as the motor loaded, the speed of a machine will be gets reduced. That's it. There is no controlling of a speed as there. Okay, but in the speed control methods, we can adjust the speed to our required value by using the different methods. Okay, so already we have seen that for the speed regulation is nothing but the ratio of no load speed to the no load speed to full load speed divided by full load speed into 100. This is called the speed regulation. So under no load condition, your motor runs at a rated value, almost rated speed, but as the full load is reached, the speed will be gets reduced. So that is called as a speed regulation. And the speed control methods will have a different speed, particular speed. If I want to run at 1200 RPM, then what should be the controlling method? So if the rated speed of a machine is 1500 RPM, okay, now I need to run at 2000 RPM. So we'll see, is it possible to run the motor at 2000 RPM if the rated speed of a particular machine is given as a 1500 RPM. Okay, then if I want to run the 1200 RPM, what parameters I need to control in a machine? So these things we have to consider. Okay, So to control that, we know the speed relation is given as n is equal to v minus ia Ra divided by k phi. So k is a constant here. There are three different parameters are available. Okay, so one is armature resistance. If I change the resistance of the armature circuit, the resistance in the armature circuit, if I vary this, the drop will be varied by keeping the voltage constant and the flux constant. This is a method one, the resistance of varying the resistance by adding some external resistance. And then the second method is I can vary the flux here. I can vary the flux so that your speed can be varied. And the third method is you can vary your applied voltage. For the DC motor, you can also vary the applied voltage, then your speed is also varied. So these are the three different methods we can use for the controlling of a speed of a particular motor. Okay, so we will discuss all this in detail. So this is the first one is the supply voltage. Okay, so speed from this equation, the speed is depends on the supply voltage and the armature circuit resistance Ra and the field flux. So by using these three methods, you can vary the speed. Okay, so for controlling the speed of a DC motor, the variation in voltage, armature resistance, and field flux is taken into consideration. And there are three general methods of speed control of a DC motor. There are three methods of speed control. The first one is a variation of resistance in the armature circuit. And this method is called as a armature voltage control or rheostatic control method. Variation of resistance in the armature circuit. So I need to include one rheostat or extra resistance into the armature circuit. So as I can change the armature resistance, then your speed of a motor can be varied. So this method is known as the armature voltage control method or rheostatic control method. And the second one is the variation in the field flux. So I can vary the current passing through the field winding. Okay, so IF, the current passing through the field winding IF is varied, keeping your resistance in the armature circuit and your applied voltage constant. In all the cases, if you take N is proportional to V minus IA RA divided by flux. So in the first case, you are going for the variation of your armature resistance. So you need to keep your supply voltage. Okay, you need to keep the supply voltage and your flux should be kept constant. Okay, and in the second case, when you are going for the variation of the flux, and this should be variable and this should be constant. RA must be kept constant, your applied voltage is also constant. Okay, and this method, so varying the flux with the help of the current passing through the field winding, varied, IF is varied, that is the current passing through the field winding is varied. Okay, and the third one, the applied voltage is constant. So armature resistance is kept constant and your flux is also kept constant, your applied voltage is varied. Then this method is called as the applied voltage control or normal voltage control method. So these are the three important elements or parameters which controls the speed of a DC machine. So these methods are called as speed control methods. These three are called as a speed control methods. Okay, we will study one by one for shunt motor. I'm not going for any compound motor because operation and everything is similar to your shunt motor or series motor. So we will discuss these speed control methods for the shunt motor and series motors. Okay. So first of all, I will consider the armature voltage control method for a shunt motor. So in this method, a variable resistor Re is put in the armature circuit, and the variation in the variable resistance does not affect, because external resistance, a variable resistor Ra is put in the armature circuit, and the variation in the resistance in the armature circuit does not affect the flux. That means your flux, we are keeping it as a constant. Okay, the flux is kept constant, and this is directly connected across the supply mains. So supply mains is also constant. I'm not going to change any supply voltage, and therefore this is a circuit what we use it for the uh, armature voltage control method. So just you see that here, this is a shunt field winding RSH. This is having only a constant resistance, and current passing through this will be IF. This is always constant, because this shunt field is connected across the supply voltage. This voltage V is constant, and therefore your current IF is also constant, but some extra resistance is added in series with your armature resistance. So if you vary this resistance, if you vary the resistance Re, okay, then there is a variation in your armature current Ia. So your speed equation will become N is proportional to V minus Ia into Ra plus Rse, and here the denominator flux is constant. This phi is constant, and your voltage is also constant. Then if you vary this armature resistance, just you see always that N is running with a rated value, because your flux is kept at a rated value. Okay, just I will remove this and apply this. Here I will write that your N is this one, V is a rated value. Your rated voltage is applied, and flux is also rated value. Rated means full load value is applied, and therefore your speed is always the rated value. Okay, so or I can write that N is proportional to your EB, back EMF. So this is a rated value divided by flux. Phi is rated value. Therefore, your N is rated value. Rated value means your full load speed, what it is given in a problem, or whenever you are going to design that problem. Okay, so here your motor is running at a rated value, then your flux is constant, V is constant. Then what I am doing here, I am adding the external resistance. The resistance value is goes on increasing. This resistance is goes on increasing. What happens now? This RSE is increased. As RSE is increased, your speed will be now decreased. The speed decreases. Okay, always the speed will be decreases from the rated value. So it is not possible to control the speed above the rated value. So always you can control the speed from the rated value. So let us assume that I will consider the N rated value. N rated value is equal to 1500 RPM. Okay. Now you are varying the armature resistance here. This armature resistance, the resistance in your armature circuit is varied, and because of this, there is a variation in the current, and the drop is also varied, and your speed is gets reduced from 1500 RPM only, and therefore you can draw the characteristics versus your for the speed versus armature voltage. This is your VA. I can consider this as a VA. Okay, so VA is nothing but your applied voltage, B minus IA into RA plus RE. This is your armature voltage. That's why this is called as the armature voltage control. So this completely, this point to this A to this B, this is called as the armature circuit. So the voltage across the armature is measured like this. And therefore, you're having the rated value. So here, just you assume that the speed is rated value. This is N rated value. And this is the normal speed N. Okay. And you are having a rated voltage. This is for the V rated voltage, VA rated value, 0. So your speed is at this point. Okay. So always the speed is at this point, and then you are varying the armature resistance, and therefore the speed is gets reduced. So this will be like this. You can control the speed. You can control the speed below this rated value always. You cannot control the speed of a motor above the rated value. This is the armature voltage control method for the shunt motor. Okay. So next here, if I want to control with the armature current. So the relationship here, armature current. So armature current, as the resistance of the circuit is increasing, as the resistance of your armature circuit is increasing, IA is always decreases. Am I right? And if you reduce that value, then your IA will be increased. If the resistance is reduced, IA will be increased. And whenever you increase the current, always the speed of a motor gets reduced. That's what we have discussed for the speed and armature current characteristics. So here, this the first line. The line 1 is the normal line for only the armature resistance RA. So as your external resistance is added, this is RA plus RE. Because of the resistance, your speed will be gets reduced. As compared to the normal case, the speed will be reduced here. Okay, and this also is indicating the same thing. From the rated voltage, as your voltage is decreased, armature voltage is decreased, then your speed will be gets reduced. Okay. So this is about the armature voltage control for a DC shunt motor. Okay, next we will discuss the same thing, armature voltage control method for series motor. So here, by varying the armature circuit resistance, and the current and flux both are affected here, as the armature connected to the series field winding. Therefore, the current in the series field winding and flux both are affected, and therefore the voltage drop in the variable resistance produces the applied voltage to the armature, and as a result, the speed of a motor gets reduced. So the voltage drop in the variable resistance reduces, and therefore your applied voltage to the armature, and as a result, the speed both are reduced. So here you can see like this, because your armature is connected in series with your series field winding. So I can call it as a series field winding, RSE, and some extra resistance, external resistance, REX is also connected, and therefore some voltage drop is taking place across this resistance, and therefore across the armature terminals VA, the net voltage will be gets reduced. As the net voltage is reduced, the speed of your motor gets reduced, and this is given by these characteristics like this. Okay, you can also here consider armature current or your armature voltage. So here with the normal condition, whenever the armature current increases, because your speed is proportional to 1 by Ia, Okay, so N is proportional to 1 by 5. The 5 is proportional to IA, and therefore N is proportional to 1 by IA. Because of this reason, now your current is gets reduced. Okay, so whenever you add external resistance also, the speed of emission will be gets reduced from your normal value, and it is always below the rated value. You cannot expect it to be the speed will be like this. This is not possible. Okay, so increasing the speed is not possible with the armature voltage control method. So always, if you goes on increasing the resistance, your characteristics will be like this. It will be varies like this only. Okay, so the speed is always below the rated value. Okay, so here also in previous case also, the speed is always below the rated value. It is varying like this. So here, this will be like this. So the speed will always be reduced below the rated value only. Cannot control the speed of a series motor or shunt motor above the rated values. So it is always below the rated value. So the main disadvantage of this armature voltage control method are, so a large amount of power is wasted in the external resistance because we are adding a resistance in the armature circuit. And the armature resistance control is restricted to keep below the rated or normal speed only. You cannot control the speed above the rated value. This is not possible with the armature voltage control method. Okay, then for a given value of variable resistance, the speed reduction is not constant but varies with the motor load. And this speed control method is used for only small motors. It cannot be useful for the large rated motors. Okay, so this is about the speed control method. Okay, so out of 3 speed control methods, we are going through only one. One is the armature voltage control method. So tomorrow we will discuss about the flux control method and the applied voltage control methods. Okay, I'll stop here. So if you have any doubts, you can ask me now.